Okay, we're going to look at azimuth calculations now, and we're looking at calculating for the sun, where the vessel took a compass bearing of the sun, and then we need to find the true bearing to find the compass error. We're given the day, the date, the approximate time, latitude, longitude, DR, the bearing of the sun, and the chronometer readings. First of all, we write down our approximate time, which is 09:15 on the 16th of July. What we then do is apply our longitude to that time. And the longitude, we look up the time in the back of the book, convert it to time, 165 degrees 24, and we find that's 11 hours 1 minute. Because longitude is east, Greenwich is least, therefore we subtract that, and now we're into the 15th of July at 22:14. We now look at our chronometer, and it showed 10 hours 22:43. Therefore, instead of using 10 hours, we use the 22 hours, because that's the 22 that we've got. It'll either be more or less the same, or it'll be 12 hours difference. So we've got 12 hours there, so it's 22 that we use. 15, 22, 22:43. It's 1 minute 10 seconds slow, so we apply that. We add it, of course. So now we know our proper time is 15th, 22, 23, 53. And we're now on the 15th rather than the 16th. So we go in the tables on the 15th at 22 hours, and we write down our GHA of the sun, which is 148 degrees 31. We also write down our declination, which is 21 degrees 26.0 north, and it's actually decreasing, as you can see there. Then at the bottom of the page, right at the bottom, we'll get our D correction, which is 0.4. We then go into the increments section at 23:53 to get our increments amount for the GHA, which is 5 degrees 58.3. We look up the 0.4 for the D, and we find the correction to apply is 0.2. So we had 21 degrees 26 minus 0.2, so our declination is actually 21 degrees 25.2. What we now do is decimalize these, and that makes our declination 21.4. Then with the GHA, we apply our longitude. Now the longitude is east, so when we're going from GHA to LHA, longitude east, Greenwich is least, therefore we add it. Therefore our LHA is 319 degrees 53.3. Again, we decimalize that. So we now got a value for LHA, declination, and of course our DR latitude. We then go into the tables, the table A first, and along the side of the table A, we name this opposite to the latitude, except when the hour angle is between 90 and 270. Well, our hour angle isn't between 90 and 270, so we're going to name A opposite to latitude, so that makes A south. Now, our latitude is 68 degrees 15, and our LHA is 319.53. So we go along the top to 319.320 for the LHA, come down to 68 degrees, 68.15, and we'll find it stops at 60 degrees at the bottom. So then you find other tables a bit further on for table A, table B, and you'll find that they go from latitude 60 to 83. So again, we look up our LHA of 319, and we go down to our latitude of 68 degrees, and with a slight bit of interpolation to do there, and we find a value of our table for latitude for table A of 2.98, and that's named south. We go into table B. Table B is always named the same as declination, so that's north. Now we go into table B, and we go in with our LHA again along the top, and then we come down with our declination at the side, and we find that our value for B is 0.61. One's south and one's north, so we subtract one from the other because they're named differently, and our value for C is 2.37, and that value is going to be named south because south is greater than north, and it will also be named east because LHA is more than 180 degrees. So we then go into table C and find a value of 2.37. So here's table C, and we need to find 2.37. We'll go along the top values, 1.2, and we've got 2.36 and 2.4 at the top there, and then we go down to find our latitude, and we find that by slight interpolation we get 48.7 degrees. So as I said before, that's south 48.7 degrees east. So if we were to make a little sketch of that, we're going from south to east. So we're going from south 47.8 east. South is 180 degrees, so we subtract the 48.7 degrees because we're going towards the 90. That's 180 there, and that's 90. Therefore our value is going to be a true bearing of 131.3 degrees, which is the difference between 180 and 48.7. Now that's a true bearing. We found, we were told that the sun bore 145 degrees compass. So therefore our compass error is the difference between the two, and we found that our compass error is 13.7 degrees, and it's named west because the compass is best, the compass is most. Now we need to find the deviation, and we know that variation and deviation give you compass error. We know compass error, which is 13.7 degrees west. We're told that our variation is 7 degrees west. Therefore the combination of variation and deviation gives you compass error. So from that it would follow that the deviation is going to be 6.7 west, because we need to total 13.7 west. So that would be the deviation answer in this problem. Now we've used the ABC tables from Norris to do this. You could also use the formulas, and it mentions this in your book. A would be tangent of the L latitude over LHA, named just as we did before using the tables. B would be tangent of declination over sine LHA, again that's named the same as declination. C would be the difference between the two and named the greater of the two. And then the tangent of the azimuth is going to be 1 over this C value times cosine of latitude, and that will give you the same value. So you could use either the ABC tables or these three formulas here, and that would apply whether you were getting the azimuth for the sun, planet, star, any of those. You could still use that formula.